In this video, you'll work out the shortest path between 2 points on the sphere when represented using the Mercator projection. First of all, we will work out what the shortest distance between any 2 points on a sphere is. The answer, of course, will be given by the great circles, but let's just prove this result. So we want to work out the variation of ds, where s is arc length, is 0. That defines the geodesics. Now, we're going to use three-dimensional vectors, and we're going to assume the sphere is of radius 1, so norm x is equal to 1. Let lambda be a parameter, and let dot mean d by d lambda. Then dx dot dx is ds squared, and therefore x dot squared is ds by d lambda squared, and so the integral ds is the integral of norm of x dot d lambda. And so we want to vary this on the surface of a sphere of unit radius. We have the constraint that mod x equals 1, so what we'll look at is the integral root x dot squared, that's the same thing as that norm, minus mu times norm x squared d lambda. So mu is a Lagrangian multiplier which implements the constraint that norm of x squared is a constant. So let's call that thing f of x and x dot. The Euler-Lagrange equations tell me that df by dx dot is df by dx. So that tells me that the total derivative of x dot over root x dot squared dot is minus 2 mu x. At this point, lambda could be any parameter along the curve, so let's take lambda to be arc length itself. And then from this relationship here, you'll see that norm x dot squared is 1. So this thing becomes x double dot is minus 2 mu x. Now x squared was equal to 1. Differentiate that, I get x dot dotted with x is equal to 0, and differentiating a second time gives me x double dot dot x is equal to minus x dot squared, and that's minus 1. So take this equation and dot with x. I'm going to get x double dot dot x, and that's equal to minus 1, and that's minus 2 mu x dot x is minus 2 mu. So this equation is x double dot plus x is 0. That vector equation. This is easy to solve. The solution is x is a cos s plus b sin s. But we also must make sure it satisfies this constraint. If we take s equals 0, you're going to show that a squared is 1. If we take s equals pi by 2, that shows b squared is equal to 1. So a and b are unit vectors. If we take s equal to pi by 4, that shows 1 over root 2 a plus b all squared is 1. And s equals minus pi by 4 shows that 1 over root 2 a minus b all squared is equal to 1. So if we write that out, that's a half into a squared plus b squared plus 2a dot b. And this one is a half a squared plus b squared minus 2a dot b. If you subtract those two things, you end up with a dot b equals 0. So a and b are unit vectors which are orthogonal to each other. There's A, there's B, and the condition that x is A cos s plus B sine s has norm x equal to 1. That is just this circle here. Let's define n to be the cross product of A and B, then clearly n dot x equals 0. So geometrically what we have is the intersection of a plane passing through the origin, that's a plane, through the origin with normal n. The intersection of that plane with the unit sphere. So that gives me a great circle. Next, let's introduce coordinates. Let's set x to be equal to cos lambda cos phi, cos lambda sine, and sine lambda. So we have our sphere here, we have the equatorial plane. We're going to measure points using these coordinates. So take a line here. That angle is the azimuthal angle. And lambda here is the latitude. Now we can work out dx. That's going to give me minus sine lambda d lambda so dx squared. These two vectors are orthogonal to each other, so I just get that squared. Now this is actually sine squared plus cos squared. This has unit magnitude, and this one, that's 0. Cos squared lambda in there, which I can write as omega squared times dx squared plus dy squared, where the azimuthal angle I now write as x, and dy is d lambda times sec lambda, and omega is cos lambda. So integrating that, we get y is equal to log sec plus tan. So that is ds squared. Now if you have ds squared is omega squared ds tilde squared, then the metric given by this thing here, which is ds tilde, has the property that any angles measured using that metric are the same as the angles measured using this metric, because this factor omega squared just scales the x and y directions in the same proportion. it's a fact that every two-dimensional metric is locally conformally flat, and that's what this condition here is. Let's go back to this condition here. We have x dot n is 0. So that gives me lambda n1 cos phi. Or if I rearrange that equation, I can rewrite that as r sine azimuthal angle minus some alpha, and then dividing through by minus n3, we get a sine of this thing is equal to tan lambda. So that's the equation of a great circle. Let's consider the great circle passing through 2 points. So we're going to take the latitude and longitude. We want to find a and alpha such that this equation holds at these points here. So I end up with a sine tan lambda 0 tan lambda 1. And I need to solve this for a and alpha. What I'm going to do is use the cos of the difference is cos plus sine. I'll call that thing C0, C1, S0 and S1, and I'll call that quantity capital delta. So this tells me that cos delta minus S0 S1 all squared is C0 squared C1 squared is 1 minus S0 squared 1 minus S1 squared, because cos squared plus sine squared is 1. So here we get S0 squared S1 squared minus 2 S0 S1 cos delta plus cos squared delta is 1 minus S0 squared minus S1 squared plus S0 squared S1 squared. Those cancel off. Move these terms to the other side. S0 squared plus S1 squared 2 S0 S1 cos delta. Move that over the other side. 1 minus cos squared is sine squared delta. Multiply both sides by a squared. A squared S0 squared from this equation is tan squared lambda naught tan squared lambda 1 minus 2 tan lambda naught tan lambda 1 cos delta is a squared sine squared delta. So a is the square root of tan squared lambda naught plus tan squared lambda 1 minus 2 tan lambda naught tan lambda 1 cos delta divided by the modulus of sine delta. We take the positive sign here because this equation is invariant under a goes to minus a and alpha goes to alpha plus pi. So without loss of generality, I can always assume that a is greater than or equal to 0. And then once I've got a, I can just rearrange one of these equations to give me a sine inverse tan lambda naught over A to give me alpha. So given our two locations, I can find A and alpha, and then what I can do is draw a graph with y equals the logarithm of sec lambda plus tan lambda, which is the logarithm of A sine x minus alpha, and that was the tan. Sec is the square root of 1 plus tan squared, sine squared x minus alpha, square root there. So what we do is we plot this, say, for x between 0 and 2 pi. And we'll get some graph. We can then superimpose this on the Mercator map, provided that we make the width the same in both cases, and the Greenwich meridian will be at x equals 0 and goes out to 2 pi. When we do this, we must preserve the aspect ratio of the graph and the Mercator map, because we want to preserve the angles in each case. As an example, let us take Sydney, Australia. For Sydney, Australia, we know that the latitude and longitude, well, longitude and latitude in this case, is 151.2093 degrees. The latitude is that. For Santiago in Chile, minus 70.6737 degrees and minus 33.4475 degrees. So these are almost on exactly the same line of latitude. We get A as 1.86306 and alpha is minus 0.87104, and that's measured in radians. So plotting this with these parameters gives the graph on the screen at the moment. Now we wish to superimpose this on the Mercator map, and this is our result. So what you'll notice, instead of the shortest path between Sydney and Santiago on the Mercator map, it looks as though it should be a straight line, but in fact it is a curved path passing to the south of New Zealand.